First glimpse of galaxies far, far away as NASA's new Webb telescope releases its first images from the deep universe.
Now, galaxies that are far, far away have gotten a little bit closer. Yeah, there are dazzling images from the James Webb Space Telescope that were recently unveiled.
The James Webb Space Telescope has shattered long-standing assumptions about the nature of the early universe by revealing the existence of highly complex galaxies that existed more than 13 billion years ago, right after the Big Bang. The telescope, equipped with state-of-the-art infrared instruments, captured images of galaxies that not only exhibited intricate spiral arms, but also hosted supermassive black holes at their cores. These findings are shocking because they defy the previously accepted timelines of galaxy formation and stellar evolution. According to existing cosmological theories, such complexity would require billions of years of cosmic evolution to form. However, the galaxies observed by Webb demonstrate levels of organization and maturity that conventional models do not permit at such an early stage in cosmic history. When Webb focused on distant galaxies located hundreds of millions of light years away, it detected the signatures of elements such as carbon, oxygen, and even iron, which indicated that multiple generations of stars had already formed and died. The presence of these heavy elements suggests a rapid cycle of stellar birth and death, which runs counter to the slow, gradual development predicted by standard theories. This level of chemical enrichment indicates that the early universe was far more active than previously believed, hosting dense regions where stars could form, evolve, and explode within extremely short timescales. Furthermore, the detection of supermassive black holes in these ancient galaxies adds another layer of mystery. These black holes possess masses equivalent to billions of suns, far exceeding the size that should have been possible given the young age of the universe at the time. Current black hole formation models rely on gradual growth through accretion and mergers over long periods, yet Webb has discovered fully formed supermassive black holes in galaxies that existed mere hundreds of millions of years after the Big Bang. This discovery raises questions about whether unknown mechanisms may have accelerated black hole formation in the early cosmos. The implications of these observations are profound. Some scientists have begun to speculate that dark matter, an invisible and mysterious substance that constitutes most of the universe's mass, could have played an even more crucial role than previously assumed. It is possible that dark matter acted as a gravitational framework, rapidly organizing gas and dust into galaxies at speeds far beyond what traditional models suggest. If dark matter facilitated such rapid formation, it may need to be considered not just as a passive force, but as an active participant in shaping the cosmos. Adding to the intrigue, Webb's discoveries were not isolated. Follow-up observations detected multiple mature galaxies scattered throughout different regions of the sky, implying that this phenomenon was not a rare anomaly, but a widespread occurrence in the early universe. The consistency of these findings suggests that the early cosmos was far more dynamic and efficient at forming structured systems than previously recognized. Webb's ability to capture infrared light, which is capable of penetrating cosmic dust clouds and revealing the faint red-shifted glow of ancient galaxies, has been instrumental in these discoveries. The telescope has functioned as a time machine, peering deep into cosmic history and revealing galaxies that defy every expectation. The presence of organized rotational dynamics in these galaxies, with velocity gradients resembling those of modern galaxies, suggests that gravitational equilibrium and galactic maturity were achieved almost instantaneously on cosmological timescales. Additionally, Webb detected emission lines in these galaxies that do not match any known atomic or molecular transitions. This unexpected finding has led to speculation that the lines could originate from exotic particles or phenomena such as sterile neutrinos or interactions from the dark sector of the universe, both of which have remained elusive in particle physics experiments. Other researchers suggest that these lines might indicate quantum gravitational effects at work in the high-energy environments of the early cosmos. Webb's deep field surveys have also uncovered enormous cosmic voids surrounding some of these galaxies, revealing a level of matter segregation that was never anticipated at such an early time. These voids suggest that the process of cosmic structure formation, involving the aggregation and separation of matter, occurred much faster than predicted. The pace at which the cosmic web, the vast network of filaments and nodes that connects galaxies, emerged appears to be at least 10 times faster than theoretical simulations had anticipated. The telescope's findings go even further, detecting intense ultraviolet and X-ray emissions from these early galaxies. These emissions exceed what would be expected from star formation alone, hinting at the presence of extreme objects like ultramassive stars or quasars operating at energies that defy theoretical limits. The correlation between infrared observations from Webb and X-ray data from other observatories reveals that some ancient galaxies were already hosting active galactic nuclei, powerful engines powered by supermassive black holes consuming surrounding matter. Moreover, gravitational lensing has helped confirm the presence of these galaxies by magnifying their light through the gravitational gravitational pull of foreground galaxy clusters. This lensing has revealed hauntingly beautiful images of galaxies that show nebular tendrils, rotational arms, and dust lanes, features that were expected only in much later cosmic epochs. The existence of such mature galactic structures forces a complete rethinking of how early matter organized itself in the cosmos. Some researchers have even begun to question fundamental aspects of physics, including the nature of time itself. Speculative theories have emerged suggesting that time may have flowed differently in the early universe, particularly under conditions of extreme energy and gravity. According to such ideas, processes that appear to have occurred instantaneously from our perspective may have taken much longer locally due to relativistic effects. Another perplexing aspect of Webb's findings involves the detection of molecular signatures associated with water vapor, carbon dioxide, and complex organic compounds such as polycyclic aromatic hydrocarbons in these ancient galaxies. This level of chemical sophistication was not expected to appear so early, raising new questions about the universe's ability to generate life-supporting environments. The presence of organic molecules suggests that the ingredients necessary for life may have been common in the early universe, potentially allowing life-friendly conditions to arise far sooner than anyone had imagined. Webb has also detected peculiar fluctuations in the background light surrounding these ancient galaxies. These anomalies do not match gravitational lensing effects or known cosmic microwave background features. Some scientists propose that they may represent electromagnetic signatures of gravitational waves originating from the mergers of dense galactic systems or collisions involving primordial black holes. If confirmed, these would constitute the first electromagnetic evidence of gravitational wave phenomena from the earliest epochs of the cosmos. Adding to the mystery, some of the observed galaxies exhibit temporal variability in their brightness. This time-dependent behavior may reflect dynamic processes such as flickering quasars, supernovae, or even coordinated astrophysical phenomena governed by as-yet unknown physical laws. The patterns of variability seem to exhibit surprising degrees of synchronicity across vast distances, suggesting that unknown fields or forces may have shaped the early universe in ways not currently understood. One of the most stunning revelations is the discovery of vast intergalactic bridges composed of hydrogen gas, connecting distant galaxies across unimaginable scales. These bridges appear to serve as conduits for matter transfer, funneling gas into galaxies and triggering waves of star formation. This interconnectedness suggests that early galaxies were not isolated entities, but were embedded within a communal network of matter exchanges that shaped their growth and evolution. Webb's sensitive instruments have also identified compact, ultra-massive star clusters nestled within the bulges of ancient galaxies. Unlike typical globular clusters, which are thought to form in single bursts, these star clusters contain populations of stars with varying ages. This finding indicates that early star clusters may have formed through a series of rapid overlapping star formation events fueled by plentiful reservoirs of cold gas. Such rapid recurring episodes of starbirth challenge conventional models of galactic evolution. The telescope's deep field imaging has revealed that early galaxies were already arranged in large-scale structures resembling the modern cosmic web. This organized distribution suggests that the cosmic scaffolding underpinning today's universe may have been established far earlier than previously thought. The seeds of this structure may have been planted during the inflationary epoch or through unknown mechanisms that accelerated matter coalescence beyond standard predictions. Thermal mapping of ancient molecular clouds has further perplexed astronomers. The temperature profiles of these clouds appear surprisingly uniform, contradicting expectations of high thermal variability in the young universe. Some researchers have hypothesized the presence of an exotic background heating mechanism, possibly linked to early forms of dark energy or unknown radiation fields, which could have maintained higher than expected temperatures in the intergalactic medium. Additionally, Webb's observations of polarized light from ancient galaxies reveal remarkably coherent polarization patterns that challenge standard cosmological expectations. These patterns suggest the existence of large-scale aligned magnetic fields or other anisotropies in space-time itself. Some theorists speculate that these observations could be remnants of pre-inflationary conditions, potentially providing evidence of a universe that existed before the Big Bang. Webb has also detected regions of dense molecular gas that have yet to collapse into stars, known as dark nurseries. These gravitationally bound regions exhibit a surprising resistance to star formation, possibly due to a delicate balance between turbulence, magnetic pressure, and the influence of dark matter. Such areas may act as pressure cookers, holding back stellar birth until precise conditions are met. Perhaps the most intriguing aspect of Webb's ongoing mission is its potential to uncover signs of habitability in the earliest epochs of the universe. Atmospheric studies of ancient exoplanets have revealed transmission spectra indicating the presence of water vapor and carbon dioxide, suggesting that planets capable of supporting life may have existed more than 11 billion years ago. ago. This raises the tantalizing possibility that life had far more time than previously assumed to emerge and evolve in the universe. In light of these groundbreaking observations, scientists have begun reworking traditional cosmological models. Revisions to the standard lambda cold dark matter framework are being proposed to account for accelerated early galaxy formation, altered initial density distributions, and enhanced mechanisms for gas cooling and black hole formation. Some researchers are even exploring modified gravity models, proposing that the fundamental behavior of gravity itself may have differed under the extreme conditions of the early cosmos. Radical theories, such as the notion of a cyclic universe in which the current cosmos is the rebirth of a previous one, are also gaining traction. Webb's findings are prompting serious consideration of these possibilities, as they offer alternative explanations for the mature structures observed at impossible redshifts. Though still speculative, such ideas may gain greater acceptance as more data continues to challenge conventional views. Educational institutions and research organizations worldwide are rapidly adapting to accommodate these discoveries. Academic courses in astrophysics and cosmology are being restructured, while specialized conferences and interdisciplinary collaborations are forming to interpret Webb's findings. The telescope's impact is extending beyond astronomy into fields such as particle physics, chemistry, and even philosophy, reshaping how humanity understands its place in the cosmos. With each new observation, the James Webb Space Telescope continues to redefine the boundaries of what is known about the universe. Its ability to reveal complex, interconnected phenomena in the earliest moments of cosmic history demonstrates that the universe may be far more efficient, dynamic, and interconnected than previously imagined. The mysteries uncovered so far represent only the beginning of what promises to be a transformative era of discovery. Webb's capacity to translate faint whispers of ancient starlight into profound revelations about cosmic origins is unmatched. Every new image and data set captured by the telescope pushes the frontiers of human understanding further into the unknown, sparking debates and inspiring fresh lines of inquiry into the fundamental workings of the universe. As the telescope continues to probe deeper into space and further back in time, it is expected to uncover even more astonishing phenomena. Whether it is the detection of ancient civilizations, the discovery of cosmic structures beyond current imagination, or the observation of exotic physical processes that challenge the very foundation of physics, Webb has shown that the universe is far more intricate and awe-inspiring than anyone could have anticipated. Ultimately, the James Webb Space Telescope has shown that every photon of ancient light carries a message, one that speaks of a universe far richer, more complex, and more mysterious than previously known. Its revelations are only just beginning to reshape the scientific, philosophical, and cultural understanding of the cosmos. In doing so, it has not only deepened humanity